and he will present the dynamical core of the Met Office unified model.
Okay, thank you. So I'm going to give a brief overview of Endgame, particularly some of the features of it, and I'll also show some of the latest results we've been getting. So this is work been going on over a number of years, and it's not just the dynamics research of Met Office, but increasingly large number of people involved in the testing, and particularly as we go to physics testing and things. And also, she mentioned the contribution of John Fuber, who's put a lot of work into this. Okay, so what is Endgame? What are the motivations behind it? So first of all, it's building upon the foundations of the current dynamical core of the unified model, the new dynamics, with the aim of keeping what's good from that, but then trying to improve on a number of areas where it's not working so well. In particular, we've got three main goals in building Endgame, which are to improve the stability of a model, improve the accuracy, whilst at the same time maintaining and improving efficiency. So I'm going to talk about the changes we've made and the results in terms of these three sort of goals to improve accuracy, stability, and scalability. So first of all, I said it's built upon the new dynamics, so important things are what hasn't changed, so what do we think are good about it. So particularly it uses the same equation set in variables, so this is a deep atmosphere, non-hydrostatic. In particular, there are a couple of prognostic variables, Exner pressure and potential temperature. We use the same grid staggering, so this is a Arakawa C grid and a Charney Phillips in the vertical. This is mainly chosen to give us good dispersion properties. Semi-implicit semi-Lagrangian scheme, it's not mentioned there that it's still a latitude-longitude grid, that hasn't changed. And the other important thing is that the physics and data assimilation scheme are going to remain the same, at least initially. So this is purely a dynamics change, so if something's changed in the results, it's easier to attribute it to probably something changing with dynamics, whilst if we change the entire package, it's a lot more complicated. So that's what we kept the same. So now I'll start going through a few of the things that have actually changed in Endgame. So we've got an improved iterative solution procedure. So this is trying to make it more implicit, so approaching a Crank-Nicholson scheme. And going with that is we've reduced the off-centering in the semi-implicit scheme. So the new dynamics has to run with a large amount of off-centering for stability, which, as Kevin mentioned earlier in the week, damps the gravity waves in particular. Whilst Endgame doesn't need that, so we can run a much more centered scheme, or if we wish to increase the damping, we could run with a higher off-centering. We also resolve a number of issues with the new dynamics, which we think aren't good or inconsistent. Particularly, again, Kevin mentioned this in his talk, this non-interpolating vertical advection of theta. We've moved to a full 3D semi-Lagrangian interpolation. The Coriolis terms are now handed as part of the iterative implicit scheme instead of being explicitly handled. And the departure point scheme, trajectory scheme, is no longer extrapolated. Instead, it's handled again in a more centered implicit way. And all these go together to try and improve the stability and the accuracy of the model. And I'll come to some results later which hopefully show some of these benefits. So I mentioned the iterative approach. One of the things it gives us is a much simpler Helmholtz problem. So for each grid point, we now only have a 7-point stencil instead of a larger 45-point stencil of new dynamics. Main gain that gives us is a much simpler preconditioner, which reduces the communication, so greatly improves the scalability of the model, and I'll show some results showing scalability later. I mentioned the non-interpolating theta advection has been replaced by full semi-Lagrangian. The other thing is that the new dynamics has an Eulerian continuity equation plus semi-Lagrangian for the other variables. Endgame has now gone to full semi-Lagrangian for all variables, including continuity equation, and this gives the benefit of increased stability, particularly around the pole, where the new dynamic seems to suffer quite a bit, which we believe is due to this Eulerian continuity equation. The Coriolis terms mentioned and handled more implicitly. Beyond that, they're also based on mass flux variables now, which improves the Rossby mode propagation. So again, this is giving us better accuracy. Also, on the previous slide, I mentioned this semi-Lagrangian continuity equation. One of the big benefits this seems to give us is that we can now run without any polar filtering or horizontal diffusion in Endgame. And the only control that we have is a implicit damping on the vertical velocity near the lids of the models and also at the poles, because we do generate sun noise there. And this is very simple to implement at basically no extra cost to the model. So this removing and filtering and diffusion again gives us better scalability and accuracy. So the final thing that changed, so I mentioned use the same latitude longitude grid. That's not exactly true. We've shifted what we store at the poles of the staggered grid from storing our vertical velocity and scalar variables to storing the v velocity now. In particular, this means we're not solving the Helmholtz equation at the pole, and this is a good thing. The pole's a singular point, so you kind of want to avoid having to do too much there. It also improves the energy properties, and again, this all goes to improving the scalability and accuracy of the model. So here's a quick diagram just showing this change in grid. So this is a new dynamics grid. We're looking down at the pole, so for instance, this is the North Pole here. And there you've got the scalar velocity point, the red one, which is involves the pressure, and then half a grid length away, you have your V winds, then half a grid point away, you have your first full row of sort of pressure, vertical velocity, then staggered U winds. Endgame has a very simple shift in that now we have V there, and then half a grid length away, we have our first row where we're going to solve the Helmholtz problem. This, as mentioned there, is a very trivial change to the grid. It turns out this is a huge amount of work in the code, and it's probably been most amount of work, I think, outside of the actual dynamics, getting everything else running with just a half grid length change. I feel I should probably show some equations, or I might get hounded out of a meeting. So, I mentioned before, we're solving deep atmosphere non-hydrostatic equations. These are three components of the momentum equation, continuity equation, thermodynamic equation. I just want to show these to bring up a couple of points in that Endgame is a switchable scheme. So although it's formulated as deep atmosphere non-hydrostatic, it can run in the quasi-hydrostatic mode or shallow atmosphere mode. So we flip a switch, we lose a green term, and we have a quasi-hydrostatic or hydrostatic mode. Flip another switch, and we lose these red terms and get the shallow atmosphere approximation, where all these R's are just replaced by the Earth radius. That gives a big benefit for the testing, and I found it particularly useful when we went to DC MIP project in the summer, which Christian and James talked about yesterday, and that then we could try running the tests in both hydrostatic and non-hydrostatic mode. So now I'll just talk briefly about the target discretization. I won't go into too much detail here, but just try and show you what we do. So our target scheme is this. So we have a trajectory equation we need to solve for the semi-Lagrangian scheme, and a prototypical prognostic equation for variable f. So the Lagrangian derivative, some nonlinear function of the variable, and slow and fast physics forcing terms. So we discretize that in the semi-implicit, semi-Lagrangian way. So derivative along the trajectory involves arrival point, departure point, and then this term gets discretized in the previous time level and the next time level. Right-hand side is average along the trajectory in a centered manner. So trajectory equation involves the new time level, velocity fields, and previous ones interpolated departure point. Then nonlinear terms just averaged again, and then the physics terms are evaluated at the next time level for the fast terms and previous time level for the slow terms. This is rewritten exactly by pulling off a linear kernel of a reference state of some kind, f, and rewritten. So we have our terms involving fn plus 1 here, this linear kernel, and then this term cancels out exactly with this term here. And then you can see the physics terms come in here. In particular, all the terms which are evaluated at the departure point are grouped into one. So we just form one interpolation. And what's going to happen is when we come to a time-stepping scheme, we're going to solve in an iterative way, in that this term is going to be replaced by the latest iterate, and then these terms here, which are evaluated at time level n plus 1 at a previous iterate, such that at convergence, when the iterates agree that this linear kernel here, we'll cancel with this one, and we will get a fully centered scheme. So this is a brief diagram of what we actually do in the time-stepping scheme, and I'll just try and briefly explain it. Start off, set your n+1 variables to be your n, so your first guess. Solve the trajectory equation using your latest estimate, the velocity field, to get a departure point. Using these latest terms, get a predictor for f. This will be used for the fast physics terms. And this involves doing the interpolation to your departure point. Then we go into what we call the inner loop, where we rewrite it in the term I had before, but now we have these n+1 terms are at the two different iterates. And we solve this a number of times, so we go around here, getting better and better estimates for the new time level. Then after a certain amount of time, we come out of here, got a better estimate for this time level, in particular for our winds at the predicted time level. So let's recompute the departure point, go through, do some more interpolations, more predictions for the physics, go through here and solve this a number of times. In theory, you could go through this as much as you wanted. In practice, we do 2 lots of these inner loops, 2 lots of these outer loops. So this gives us 4 solves of a Helmholtz equation per time step, and 2 departure point computations and interpolations per time step. Okay, so that's briefly how Endgame works, and I'll try and show you that it does work and show some results. So these first ones are some aquaplanet results. So these are plots of the eddy kinetic energy. On the top we have new dynamics, below we have Endgame, and this is just trying to show that Endgame is a much more active model, produces at the same resolution much larger kinetic energy, but new dynamics seems to be a bit more damped, and you can see the difference here. In particular, in this test case, that Endgame at this N48 resolution is approximately equivalent to the new dynamics at twice the resolution. So this next plot is a summary of the errors we get in a number of high-resolution NWP test cases. So these are just initialized from ECMWF analysis, and you don't need to understand all of this, but basically we're looking at a very large basket of measures. We're comparing it with the new dynamics run, and so everything that we increase the RMS error, we're doing worse at, so worse on these. Everything we decrease it, we're doing better at, so these are all better. And in particular, the important thing from this is basically we're looking at around 300 measures. A large amount from almost 200, we're pretty close, we're not changing much, and then about an equal number, 50-ish, we're improving, but also doing worse at. So just zooming in at a couple of points where, for instance, we're doing a bit worse is these measures which are increasing error, it seems to be saying we've got slightly worse northern hemisphere. These ones up here, these are all high-level temperature fields. This seems to go with a lower stratospheric warming that we have in Endgame compared to new dynamics. And to mention, these are both sort of related, so if we made this better, these would get worse. So it's not as simple as just being able to reduce one. So I mentioned some of the extra accuracy Endgame gets, particularly the off-centering of the semi-implicit scheme. So this is very similar to a plot I think Kevin showed earlier in the week. In particular, this is vertical velocity high up in the atmosphere in a high-resolution run, with the new dynamics on the left, Endgame on the right. We know new dynamics doesn't have these gravity waves down here, which do appear in the observations and in the ECMWF analysis compared to. Endgame does have these in, and this is purely due to the reduced off-centering that we have in the semi-implicit scheme. And in particular, if we increase the off-centering, which you can do in Endgame, we can just make these disappear, and we get a much more similar picture to this. But you can't go the other way in new dynamics and reduce it because it becomes unstable. Some more tests we've been doing recently, these are AMIP 10-year low-resolution climate runs. I'm not going to go into too much detail about them. Just want to mainly point out this plot, which is the difference in fields between Endgame and the new dynamics. And although there's lots of white areas here, to point out this is a logarithmic scale, so some of these changes are quite large. And there's just a couple of good things that we want to point out is that endgame is giving increased precipitation over India, so more powerful monsoon, which is a good thing. Also giving decreased precipitation over the ocean and over Central America. These again are problems we have in the current model, which seem to be improved under endgame. And then here's plots of biases, and this is just trying to show that in this case it has reduced the RMS errors. As before, for the NWP cases, we're looking at a very large number of measures of error. So this is a very similar plot in that this is RMS error again compared with new dynamics current run. So if we increase it, we're doing worse. If we decrease it, we're doing better. And these bars show the observational range. So in particular, you can see some red crosses, we're doing worse. We've made things worse than new dynamics. And then some green crosses where we're doing pretty well, and orange crosses where we've improved compared to new dynamics. But sometimes we've improved, but we're still not great because we're outside the observational range, but at least it's a step in the right direction. Particularly compared to the previous slide, these ones improved are the tropical land precipitation that I mentioned. This is the same as the NWP one where we noticed worse scores, but the lower stratospheric warming that we get in endgame. Okay, so that's more about the accuracy of the model, but I'd like to quickly mention about the stability gains we get. The past couple of years, we've had the operational models have fallen over in September over Antarctica. And the characteristic of this is you get flow aligned along a ridge of mountains in Antarctica. So this is the outline of Antarctica down about 85 south. And you can see new dynamics on the top. It's got this large, these are plots of vertical velocity. It's got these large high frequency waves here. The equivalent endgame run just doesn't seem to have them. Another way of looking at that is height longitude cross section. So you can see the orography down here. These again are vertical velocity contours. You can see these large amplitude waves in new dynamics, and the model falls over very soon after this. Endgame is just a lot smoother, a lot nicer looking. And I should mention that this isn't just due to the fact that we have a damping on W in this range, because we can move that so it acts only further south than this, and that this would be a region where there's no damping and we still don't see any failures. So this really is improved stability of the model. Okay, so I've mentioned a lot about the accuracy and the stability of the model. The other thing we wanted to try and get was increased scalability. So this is a scaling plot, the runtime versus, so this is nodes on our supercomputer. So as I mentioned, each one of these nodes is 32 processors. And this is at our proposed next resolution for global model. So this is 17 kilometers horizontal run. And one of the things we're constrained by at the Met Office is we need to get the forecast out in time. Otherwise, they're not forecasts, they're hindcasts. And so we have a 1 hour time slot where we need to complete the forecasting, and for this resolution, our target run would be on 96 nodes. So we need to get the forecast done within 1 hour, hopefully on 96 nodes. If we run the new dynamics, you can see that at the target number of nodes, it doesn't make it, it's too slow. And worse than that even increasing the number of nodes, it's just running out of scaling around there. And so there's not really much hope that you'll be able to fit this resolution in this window. Endgame, however, at the target nodes, reaches it quite comfortably. And also, for the future as well, it's looking good that we're still getting scaling up to, this is sort of about 7,500 processors almost. So this is good. It gives us hope for running high resolution models in the future. So this is the same plot, just shown in different ways. So then this is scaling compared to the 24 node job, perfect scaling in blue, endgame again red, new dynamics black. You can see the new dynamics is running out of scaling at a much lower number of nodes, sort of 100, 125, whilst endgame is continuing to scale up to almost 7,500 processors, which is quite good. But you can see, and use imagination, you can see this is probably tailing off in the not too distant future. So we've improved the scalability, but we haven't got great scalability at very high numbers of processors. And this is mostly due to believe to the one thing that hasn't changed, the latitude-longitude grid we use. In particular, our current operational resolution, 25 kilometers, you have a 75-meter spacing at the pole. If we get down to 10 kilometers, which hopefully we want to do in the not too distant future, that's down to 12 meters, which is a pretty small resolution, and that gives a big bottleneck to scalability. And this has led to the Gung Ho project, which you've heard a couple of talks about from John and Colin earlier in the week, which is one of its main goals is to produce a model with a more quasi-uniform grid. So, for instance, icosahedral, some form of our cube sphere or yin-yang. And this is a project that we've joined between Met Office, NERC, and the Science and Technology Facility Council. So I won't talk much more about that, but just to say then, endgame is looking good, as shown from all the plots, but there's still quite a way to go. Still got lots more tests to do, particularly coupled ocean atmosphere tests, also trialing it with data assimilation and part of the ensemble scheme. And the aim, which I think is hopefully still true, is to get it operational by autumn of the next year. And finished, thank you.
Other questions?
Is the improved stability in September, is that due to the consistent advection of mass and temperature, do you think?
I think, I'm not entirely sure we know exactly why. I think it's more due to the interpolation. The theory is that dynamics does interpolation in physical coordinates, so in height. And then the steeplerography introduces more errors, whilst the endgame, we do it in the computational space, where the grid is more uniform. So I think it's more to do with that. Hopefully that's right.
You?
Yeah, I noticed your gravity waves at high levels seem to tilt toward the east as you go from the equator to the pole in both hemispheres. Is that thought to be the way they really behave, maybe due to some gradient static stability or something? Does anybody look at that?
Not that I'm aware of. I don't know. Probably something just to look at.
And what exactly is the implicit damping?
So it's just a Rayleigh damping layer on vertical velocity. So the so the vertical momentum equation, when we discretize it in time, we just end up with we add an extra term of some constant, height-dependent constant times w at the next time interval on the right-hand side.
So that removes the CFL. How does it act on the CFL criteria?
Sorry?
How does that act on the CFL criteria?
Oh, well, it's purely implicit, so it doesn't affect the CFL.
No need at all. Yeah, right.
Are there further questions? Okay, then we move on to a coffee break, and let's thank Tom and the speakers of the session.